Hi, welcome to the straight after lunch session wherein we all feel a bit sleepy. So it's all too much effort. So what we can do is delegate all the hard work to our machines. For example, getting it to play Snake for us. That seems like a nice after lunch activity. What I'm going to do is I'm going to give you an overview of reinforcement learning. That actually covers a huge number of different algorithms which you could regard as machine learning or AI. But I'm just going to show you a tiny little bit because that's simpler to code up and doesn't involve as much explanation. I'm going to start simply. I'm going to move in one dimension. So I'm going to be able to go left or right, and that's it. And the aim's going to be to try and make a little blob move to one side of a line. Oh, challenging stuff. And we'll look at some ways to do this and gradually introduce the idea of the little blob learning how to do this itself based on a reward. And that's the nub of reinforcement learning. And there are those who say that's how humans start learning things. That if you get a reward for something, you might get a bit of a dopamine hit and feel good. And that helps you remember, oh, that went better when I did it this way last time. So that's the executive summary of the talk. And if you want to go now or just have a little snooze where you are, that's fine. If you're still listening, that's lovely. Once we've got the hang of going left and right, we're going to move up to another dimension. So we're going to be able to go up and down as well, so we can move in two-dimensional space. And at that point, we're much closer to learning how to play Snake. There's a few little extra bits we need to get there. I'm going to demo the code in C++. You don't have to use C++. I think a lot of people say at the moment, anyone who's doing AI is probably using Python in order to implement some of the algorithms. But we all know that Python often under the hood ends up being C++, because that makes it quicker, which is fine. And actually, there's a surprising number of little bits if you try and implement a well-known algorithm where you go, oh, I'm not quite sure the best way to do this in C++. And there's a couple of slides I've got that each time I look at them, I go, that code's horrible. So if you can see better ways of implementing this, please let me know. We're all learning together. So I edit Accuse Overload magazine. If anyone writes up a blog about this conference, share it with me and I'll publish it in the magazine. I've been a programmer since last century, mostly C++ and Python, some C#, and we won't mention Perl or VB or some of the other things. I've written a couple of books. One of them, the first one, the right-hand side ones, I published about 2019. And that's got loads of examples of how to implement some machine learning and AI algorithms in real simple context, most of which involved escaping from a paper bag, hence the continuing theme now, because I've got stuck in a bit of a rut, but it kind of works. And then my Learn C++ by example book was trying to help you catch up with some of the more recent standards. Now, of course, I was writing it when 23 was happening, so there's only little glimmers of that, and C++ keeps moving. And I started writing an introduction to C++ for O'Reilly. That's really hard, so respect to anyone here who's been doing the beginner level talks. It's so difficult explaining things from the beginning. Right, I'm going to jump in the middle here. We will just go left and right first, which is quite simple. I'll see how it goes. I'm in various places. I'll share the slides later. Feel free to get in touch. So, reinforcement learning. Like I said, it's a part of AI, a type of machine learning. Like I talked about a blob moving left or right, and we'll see that happening in a moment. So you can cast it in the words of having an agent that does something. It might be moving around or exploring an unchanging or static environment. So you could do that to solve a maze or some other problem where things don't change. Or you could have a dynamic environment. I don't know, for example, if you're playing the game of Snake, then when you eat an apple, it's gone, and then it turns up somewhere else. So the same sort of algorithm can deal with both types of environments. And you could see how you could use this for something more real. You can use this kind of approach in situations involving real space, like robots exploring trying to find people buried under rubble or remote bomb disposal things. And it's that reinforcement learning that will teach them. Lots of people, when they say AI at the moment, mean Gen AI, right? So LLMs, and using AI to generate things for you. That's just one part of AI. So I'm here to remind you there's loads more to AI than just that. Has anyone used LLMs and knows something about the architecture? A couple of maybes. So you see in there the idea of reinforcement learning from human feedback in the middle of the whole architecture, which is an opportunity for you to take what the Gen AI is coming out with and tweak it and train it more towards what you want it to do. And it's based on the same principles. I'm going to show you a real simple way of doing this today. I think the LLM type stuff and various other things do tend to use neural networks, which involves a bit more maths. It's not that hard if you've done some like 18-year-old level maths at school, but it's not time for that today. We're keeping it nice and simple. You'll still get the hang of the basic algorithm though. So we're going to have a simple game. And while the game's not over, one of our agents is going to pick an action, which initially can just be left or right, and then we're going to jump to another dimension, go left, right, up and down, and it performs the action, sees what happens, and that's it. Pretty simple. So we'll start off with one agent. I think all of mine are just going to have one agent, but you could have more than one agent operating in space, and then you'll be able to solve some other types of problems. And that's the green square, starting in the middle. And the action is, like I said, left or right. If it falls off the left-hand edge, I'm going to give it a score of -1. If it falls off the right-hand edge, I'm going to give it a score of +1. At the moment, it's not going to learn anything, but phase one of the talk is we want to get it to go right in the end. So we'll have to start learning in the end, but we'll just start randomly and see what score it gets. It's that simple. So my first attempt, I want a random number that's either +1 or -1. And this is the first bit of code that I found mildly annoying. It's a bit squidged up and small, but the game runs whilst the position is above -1, which is the left-hand edge, and below the length of the line, so below the right-hand edge. So in theory, I could vary it, even though I've made it a const x and put it in the function, whatever. So we play the game and we pick an action. Now, I just want to pick the number -1 or +1 because I want it to actually move. The way I've set this up, if you're used to random numbers in C++, a few slight nods. The way I've set this up, we can get -1, 0, or +1. So I'm doing what's technically called rejection sampling. So while the action's 0, that's not a valid move. I'll just keep trying until I get a -1 or +1, which will force it to go left or right. There are other ways you can use the random numbers in C++. You can do a random choice to pick one specific thing, but then you have to say, I want to pick one thing rather than 2, 3, or 4 things and provide a container to put all the results in. So this seemed like less code for a slide. Like I said, open to discussion afterwards. But basically, whilst it's still on the line, the game happens and keeps running, and then I draw it. Just drawing it each time to see what's happening. I just did this on the console at this point, and I don't know if you tried doing this before, but you can send in some escape sequence to make it clear the screen, which does tend to work on most operating systems. I've made it work on Linux and Windows, and I understand it works on a Mac quite nicely as well. That's a bit of a ruse. He made it nice and simple. So this is just randomly picking an action. So I've got my agent, which is the cross in the middle. It's randomly doing stuff. Oh, it nearly went out. It's not learning anything, but we've got the rules here. We're going left or right. And game over. score, +1. We haven't learnt anything yet, though. So that's just done a random walk, and you would expect it to win 50% of the time. I could run some stats, and it is approximately that. We're here to teach the machine to do the work for us, or the machine to do some learning. So now, some of you might argue with me this isn't much learning, but start simple. Now, it's going to go +1 or -1, and I'm going to encode a model in my AI, or let it do something random. So it's the same as before, except now it's going to build up an environment and it's going to keep track of how many scores it got based on the model that I'm going to provide. So I'm telling the machine some information at this point. And we're going towards a point where I tell the machine almost no information, it figures it out. But there's some problem-solving ideas where you do have some upfront information about what's going to work. For example, in this case, going right might be a good idea. So I could encode a model that says, oh, if you want to pick the best action, just go right. Cheating? Yeah. And again, abusing. It feels like far too much code to put on a slide. What we're doing is we're providing this epsilon, which is a probability in the reinforcement learning literature. So when I set that to 0.1, I'm saying 1/10 or 10% of the time, just do something random, which you can see from the action that it's picking. It might do something random 1 time out of 10. And the other 9 times out of 10 is to pick the best action. And I told you what the best action was going to be. So there, I've encoded my model. That did fit on the slide nicely. And then I looked at it and thought, yeah, we've got loads of ints going on, so don't do that, and you should probably introduce a strong type. Don't worry, I'll make the code neater and more intelligent later on. So now 1 time out of 10, it's going to do something random. 9 times out of 10, it's going to use the information I've provided to the agent. So you would expect, yeah, well, there's only 5 steps. So if it's only got a 1 in 10 chance of doing something random that might be left or right, it's almost certainly going to be much quicker than the last demo, which is good because we've got more to do. Now, in theory, it could lose, but if I run it for about 100 or so, I got bored. Don't worry, I didn't then put it on the screen. I just let it spew to a file and had a coffee. That really does seem like cheating. But actually, if you step back and you do look at how some AI models work, or even some algorithms and things, if you start with some base cases like just 1 dimension instead of 3 or 4, and provide a simple model, always take a step to the right or left. I mean, it depends which way around you want to do things. You can see how you can provide some information to a model. This is really simple, but you could set up like robot vacuum cleaner and go, actually, if you feel yourself leaning forwards, then go back again, because it might be about to fall off a cliff, is what our robot vacuum cleaner says. It means it's fallen down the stairs, but it hovers and goes, well, back up. So you can provide some heuristics that way. Might always go right, wasn't a proper heuristic. Maybe it was. Right, so that was cheating. But we've got a little agent off the end of a line, so we're moving towards escaping paper bags. So now this time, instead of me having a fixed model up front, we can just let the agent move. And it can build up a table and go, oh, when I went left, this happened. When I went right, that happened. So we've got a position, which is the index 0, 1, 2, 3, or 4 of the line, and the action of go left or go right. So I've got a pair as the key to look up, and then it gets a reward. Again, -1 if it goes off the left, +1 if it goes off the right, and 0 for all the other cases. And that way you can build up, like I said, a lookup table. other lookup containers are available in C++, but then you need to understand how hashes work, and my head hurts. It's after lunch. So same as before, we're going to have a lookup table now, and we're going to reset our environment at the beginning of the loop and play the game, do an action, take a step, and this time we're going to record the results in our lookup table. And I'm not going to tell it to always go right. It's going to use the lookup table to go, well, when I was in this state before, which one looked better? And again, like we saw in the first example, it will just do that epsilon% of the time. Most of AI and machine learning algorithms, you let it do something random every now and again to keep it exploring. Otherwise, it just keeps doing the same thing over and over and won't learn. So now the best action, it looks up left, it looks up right to see what reward it would get if it were to go left from this state or if it were to go right from this state. And it goes, oh, is one better or the other better? And if they're both the same, equivocal, then we just return 0 and then it drops back to making a random choice if there isn't a clear winner there. So it's a small little change. And now our reward function, we need that to add to the lookup. So now I say, well, yeah, if you've gone too far to the left, you get -1. Or 0 if there's nothing in it, or +1 if you escape off the end. Now, because I said about using strong types possibly being better, my line length, it makes perfect sense for that to be unsigned, right? I'm not going to have a negative line length. But now I'm comparing integers and unsigned integers, and somebody should do an entire talk on that at some point. I'm sure people have done bits about this before. You know, you can use the standard comp less if you get yourself in that situation. How many times have you ended up writing code and see a warning that says you're comparing a signed and unsigned value? Pay attention to your warnings, and C++ does provide you a way to deal with this properly. You can think through the kind of message you might get in. I think with a little line of just 5, we're probably okay, but you should pay attention to warnings. How do we learn? Well, we just say the state we were in and whether we went left or right, which, like I said, should probably not be an int. We'll make it better in a moment. And then we know what the reward is, and we just add it to the quality map. So after each action, we've got more evidence about what may or may not be good. And that will reinforce the positive and negative rewards and nudge the behaviour in a direction. We've still got that epsilon random thing to keep it exploring. There isn't much to explore on a line that's just 5 long. You can make it 10 long, and we'll make it 2D in a moment. So this is not entirely clear what it's doing, but it is zinging backwards and forwards. If it escapes, it escapes. So I think this is an early run before it's been trained very much. If you run it several times, it eventually gets the hang of it. But you can see it wavering around. If we ever think about what the reward table is going to look like, we might realise that we can help it do a bit better. So it's better than random, just about. It's obviously not as good as our fixed model, but we can do better for reasons. If you think about the quality table, so only once it steps off either end of the line did it get something other than 0. Most of the time, the squares in the middle, whether it goes left or right, the reward is 0. So it is quite happy to faff around in the middle going, this is safe, this is safe, this is safe, it's all fine. And it's only if it actually gets to the edges, then it gets something other than 0. And given I want to teach my machine how to play Snake, if it's not learning anything and it's only extreme danger situations, then that's probably not going to work. Want a way to say, go right to it, and this isn't going to work unless it's just on the right-hand side. Is someone trying to ask a question, or you just... So at this point, introduce a massive book, which I'm really sad I haven't finished reading because it's got loads in there. But that means I've got loads more to read when I get a moment. It's a really good book, and it's a standard textbook on this kind of thing. One type of reinforcement learning that I'm going to show you today is going to build on what we've just done, that lookup table. It's called a quality table. So this is called Q learning, because all AI and mathsy things, we're too lazy to say whole words or put letters in, just make it as short as possible. So I'm going to show you Q learning. There are other things you can do, like you can back things. Instead of a lookup table, you could use a neural network or something more complicated. But I like the simple things to just get a flavour of what happens. I gave a talk a while ago about how to move in space. This was probably shortly after lockdown. I couldn't remember, so I thought I'd remind myself how to make agents move in space. And I imposed in advance a field, which gave them an imperative to move in one direction or another. In the case of the reinforcement learning, I'm now going to get the agent to figure out the field itself just by exploring stuff and seeing what reward it gets. Like I said, at the moment, the very left-hand and right-hand edges get the reward. We want those to kind of percolate through into neighbouring states, maybe just a little fraction of each, to just encourage them and discourage them as appropriate, rather than in advance saying go right or go up. So there are lots and lots of words behind all of this. But basically, the trick with the Q learning stuff is to look at one current state and the next state as well. So it can go, if I'm here and I were to go left, what would be the best I could achieve next time? So having that one step ahead allows you to send some of the numbers back as well and let them kind of bleed over the edges. It's called a temporal difference method, because you have the world in one state at time t and the world in the next state at time t plus 1. But that allows you to go, I know it looks shorter there, but actually if I go around the corner, then I win a gold coin or something. You just go, actually this and then this, rather than the immediate best action. It just means we're going to send an extra parameter or two into the learning function of where we were and where we've ended up. So I mentioned that. I'm going the wrong way. I'm going the right way. All of this pulls on something called the Bellman equation, which you don't really need to know, but this does make it one part of AI and machine learning, where you can actually prove some things with maths and probabilities about whether you'll find the optimum solution to certain types of problems. There are, of course, some caveats and assumptions about what kind of model you've got, but unlike some AI stuff that are just kind of stochastic guessing, you can be more precise about how close you've got to optimal solutions for certain types of problems, which is why that book I showed you is really quite big. And the Q learning gets described as off policy. So it's got the learning table, but he doesn't always use that directly. It's still got that epsilon thing, so it's still doing the random exploring. And then it updates the lookup table and sometimes uses that. There's a wall of words in there, but we can simplify it down to, don't worry about all that. We've still got the epsilon. We saw that earlier on. That keeps the randomness happening. And then there's an alpha parameter. And if I go back, you can see, so the quality in state T looks at what it was before and then adds a little bit of the reward it got next time, followed by gamma of the best maximum it can do. So if it were to go left, if it's given a choice of left and right, it goes, well, if I go left, then the next time I might get the left or right reward, and that pulls a little bit of that some step that's 2 steps, 2 hops away into the current state. So there's alpha controlling how much it gets updated by, which can, if you keep that smaller, it means it will tend to forget some things that happened a while ago, which allows you to switch between static and dynamic environments, which I won't show you all the details of that. It's just a number. And most of the numbers in these algorithms tend to be between 0 and 1. And then inside that bit, we've got this gamma, which is just how much of the 2 hops away do I pull over. And you often have to twiddle with those and see what works. And if you drop that right down to 0, then it just does the next step. It just does the reward it got from that state. So you can control whether it brings in this extra info. There's a lot of words in there. So basically, we've now got 2 extra numbers to use on top of the epsilon. And we look at the last state we were in and the action we did in the next state. And that's it. And that's going to deal with those all the zeros in the middle. This then led to more mucky code. So, I've set my alpha. So that's how much it remembers as it goes to 10%. And the gamma, I'm actually pulling quite a lot of the neighbouring states. So I want to go for my lookup table and find things that are in the next state, right? And then I want to find the potential best I can get in the next state and add that to the current state. So if I'm in the current state and I go right, then I'm going to include some of the next state I can get from the next reward I can get from right in the current one. So this one gets some of what it could get from the next one, which is going to encourage moving right and let those numbers percolate over. For example, if I drop out the numbers after another run of 100 on those, you can see that I haven't got all zeros in the middle. I'm still discouraging it from going left when it's on the left-hand edge. But for the second parameter being a 1, which is encouraging it to go right, it's always more likely to go right. And it's just because it's gone, well, if I were to go right, then I can go right and get an even bigger reward next time. So it's kind of percolated back. So we were dealing with loads of zeros in the middle. We knew the fixed model was really good. We knew that pure random would be 50-50. But now the number of steps it's taken overall has gone down because I haven't got all the zeros, so it's always more likely to go right when it's looking at the best move. Still got the epsilon there, so still got 1 in 10 might do something random. And a demo, and yeah, much quicker. Bang, bang. Once it had been trained, it's much more likely to go right. So it keeps restarting in the middle. It's still doing some random exploring. Well, it's figuring out, it's like the machine has learnt that it's supposed to be going right, just with some multiplying and adding up, really. However, we're nearly half an hour in. I'm supposed to be doing snake, and we aren't even in 2 dimensions yet. So let's do that. Now I really need to deal with my ints all over the place because it was like, oh, because if I'm in 2 dimensions, I'm going to have an X and a Y and a step and a reward. And let's actually have some proper types for a position and an action. Might make the rewards doubles now. And in fact, because as soon as we introduced things like gamma being 0.9 and stuff in the last one, I had to actually switch the lookup table from ints to doubles then. It's exactly the same algorithm, really. I've just changed the actions it can use and the reward function. But the updating the Q-learning table's exactly the same. That doesn't... The Q table itself has got a different key in it, but it's kind of by the by. The essence of the algorithm's the same. We've got a position now and a proper action and a lookup table using positions and actions and doubles. Oh, and more code that if somebody wants to discuss with me how to make my code neater, that would be cool. We're still doing the same thing though. We're finding the quality that we could get, well, the reward from the current state and the action. And then we look at the next state and see what the best possible reward is out of those, which just involves pulling things out of a map. And then we multiply by alpha and gamma as required. Yes, and the pick best actions, like, if up, down, left, right are all equivocal as to which one you do, I want to make each one equally likely, so I have a 1 in 4 chance. So I can use a discrete distribution to weight individual numbers. Are you used to the discrete distribution? It's just a way of weighting your random numbers. So it's almost like I should do a talk on random numbers in C++. I did that a few years ago, but now there's some new ways of doing things, but that one's been there for a while. So instead of up, down, left, right being equally likely, you might want to make up much more likely and give it a weighting, and the discrete distribution lets you do that. But I've got this edge case where they might all be equally likely and the discrete distribution blows up at you at runtime if all the numbers are 0, so had to deal with that. In less words, it's either going to do something random or pick the best action, just like we've had previously. Two-dimensional. Again, the code was really similar. It was just the state and the position and the lookup had changed a bit. And it's about, so it gets a reward if it goes out of the bag and if it crashes into the edges. Now it's looking a bit more like Snake. We might just about manage this. And I could show you the stats from the Q table again. Starting to get out of hand now we've got 2 dimensions. But you can see if it's on the top row, it gets more if it goes up. So it's learnt that it's getting rewarded if it goes up. Now, we're going to do Snake in the end, but that's far too hard. Do you all know the snake game? I should have said that at the beginning. So you're supposed to move a snake round, eat an apple. If you eat an apple, you get 1 longer. Well, that was far too hard initially, so I thought, all right, I'll just have an obstacle and see if it can avoid the obstacle. But that's like eating an apple is just the opposite, so I might be able to change a plus to a minus and it might just work, and I've got about 2 weeks left before the ACU conference and it will be fine. So, but we can go nice and calm now, because it did work. So now, on my grid, I've got plus sign for my agent, got the edges of the bag, and there might be an O for an obstacle. So now it's going to end if it crashes into the obstacle or hits the edges of the bag or goes out. Now, crash, restart, oh, escape, and so on. And it eventually learns to avoid the obstacle. You saw it crash into it to begin with. And it kind of went, oh, I won't do that again. Again, we've still got that epsilon, so it theoretically could. But the more experience it's got, the more it's learned to avoid the O, which has got to be like encouraging it towards the O, right? Surely. And I can drop the stats out and see how it's doing. Now, so that's like, at that point, I'm going cross-eyed. But it was a 2D grid before, so I can fill it in again. So the obstacle is where the red is, and at that point, the game's over, so it doesn't update further for the step beyond that. And you can see how we've gradually got some numbers for some of the states in there. And at that point, I'm starting to think, yeah, that's a very tiny snake game. I want a much bigger snake game. And if I record the exact position, my state table is going to get quite big. And the obstacle stayed in one place. The snake eats the apple and then it appears somewhere else. So, need to do something slightly different. Tinkering with the gamma parameter makes a bit of a difference there. Well, let's just start it playing. So this time it can eat the O, which is an apple now instead of an obstacle, and it'll grow. I can't remember whether I'd let it grow straight away or just get there one at a time. We can still use the same Q table. So we're not there yet. We're just going to change from obstacle to apple, and we might need to respawn the apple sometimes. Oh, and I've got a typo in my instructions to myself, but that's fine. What did I say? Nope. That makes sense. And it's gone off the top of the thing. Let's try again. I should have resized my windows properly. And it's crashed. Oh, God. Oh. Takes a few, goes, go on, no. Go on, no. Some of the previous stats I showed you was a run of about 100 or so. So the question was, isn't it just like spitting out, just learning the random number generator? Well, there's the epsilon that's giving it some of the randomness, but it did know that there was a hazy shadow apple in this position just now, so it's being influenced slightly. But then we can go all meta because the apple's position is also coming from random number generators. And what does learning even mean? Or is anything even random? I mean, anyway, let's leave that to it. In fact, let's not. Let's progress with the slides. Yeah, so if we've only got the position and whether we go left or right, it hasn't got everything it needs to know. So we need to encode more in that state. Right, so done the demo. And so there was lots of discussions there, and I'm really sorry, I didn't repeat all the questions. So if I've just got the position and I just go left, right, up, down, it's just going to do random stuff. If I now tell it, and I had forgotten to say that the demo I just did, at that point I've increased what's in the state. The position can include the character that's up, down, left or right. It could be blank, it could be an edge of a bag, it could be a snake shape, not that we've got there yet, or it could be the apple shape. So if I just do the position, up, down, left, right, as we've discussed, it can't see where the apple is, it doesn't know where it can guess where the bag edges are to a point. It doesn't know the bag edges. It's just a little agent. It's an AI. It doesn't know anything. It's a map and a behaviour based on a map. And if I make it into a bigger snake game, that table's not going to fit on the screen. And we can't tell where the apple was. So how did it tell where the apple was? So what we can do is I can introduce more than just the position. I could have a state. I could say what characters on a place in the screen. So the agent's in one position. I could tell it the character's up, down, left, right. And at this point, I've resorted to what felt like cheating and gave a bit of the game away. I gave it a plus or minus 1 or 0 for horizontal and vertical distance to the food. So I have leaked some of the information about what's going on here. You could do it without that bit, but for reasons, it will take a very long time to get there. If you start doing the stats on the possible states you've got, you're in trouble. So yes, at this point, we've moved on from the position doesn't tell us where the apple was, let alone the agent. So now I'm giving it clues as the horizontal and vertical displacement to the apple. And it can see the immediate surrounding characters, up, down, left and right. And I'm providing the spaceship operator so I can put this in a standard map because that fits on the slide better than talking about hashes. So that's why we're not doing an unordered map. So now I've got more than just the position. It can now see, our agent not only is learning, it can see up, down, left, right, and it's got a sense of which direction the food is, which does feel like cheating. So now we can play snake. Now, I'm going to stop encouraging it to get out of the paper bag because I couldn't quite work out how to combine that. But we can see that it got out the bag. So, again, that's open to discussion. So, it can move, it can check whether it's eating the apple, it can spawn. And a nice way of implementing snake, and it's one of the few uses of deck that I've seen that I found compelling. Use to deck, like a vector, but it's in pages. And the snake wants to, if it's going to move forward, wants a new head, pop the tail. Unless it eats an apple, in which case, new head eats the apple, tail stays where it is, which allows you to grow the snake really efficiently. I like that. Thanks to several friends I've got who are games programmers. So the snake is just a deck of positions, and then that makes it really easy to make it one longer when it eats the apple. And now I can slap the environment around this. It's very similar to the two-dimensional and one-dimensional things we saw before, but we're using a different Q table. It can now see things up, down, left and right, and it has an innate sense of the displacement to the food, because I told it. And I'm leaking the whole game so that I can draw it as well. But there's still the same steps as we've seen before. It plays the game and finds out if it gets a point or not. Obviously now it's going to lose a point if it crashes into itself and get a point each time it eats the apple. I could go better than that. I could go -2 for game over, +2 for eating the apple. And I could also say -1 if it moves away from the food, or +1 if it moves nearer the food. Now, see, too many stats to look at. There was something in there that was useful. I don't know what it was. Yeah, well, we can see where the apple is now, so you can see the zeros in the middle column, whereas last time we didn't have a clue where the apple was, which one of you pulled out. I should have had that on my slides. I wonder if this will work. Not if I start in the wrong folder. So if I drop the Q table out at the end of each session, I can then pick it back up again. It can just continue as it was. And in the process of developing this, I realised while I didn't spawn the apple somewhere there wasn't a snake, I would try again. I thought it's hung. And I thought, actually, no, it's just filled up the entire grid. So it's done really well sometimes. But you can see it's doing something. I suspect it's not going to eat the apple this time. Nah, it crashed into itself. It was so desperate to get to the food. But now I could leave it training on a much larger grid that's just those characters from the console. I don't even need to write out to the console. And then I can point it at an actual snake game. And as long as the snake game can translate the character of, like, oh, that's the colour of the edge of the screen, or that's the colour of the snake body, or that's the colour of the apple to the characters I used, we can play snake. And we actually can if I get the right thing. Oh, no, I'm not with it. Oh, you naughty thing. So it does that sometimes. I haven't got to the bottom of why it's doing that. And once it does it lots, which is very odd. It's those who came in first. It didn't do that. That's very odd. Don't know why it's doing that. It's going to do it again. Oh, it's going up and down this time. My goodness. Oh, it doesn't make sense.
If you're popular, it does. The food's still there. It's trying to take it again.
So what I've done is, in order to resize it, of course, I've made the lines too long, and it's actually not sitting on things properly. Was I doing something different before anyone turned up? Goodness me. That's better. It does seem to do that sometimes, and I haven't got to the bottom of this, so you just go backwards and forwards loads. And it gets stuck in it for a little while and gets over it. I haven't got a clue what's going on there, and if anyone can think what I might be doing, that'd be really interesting. I guess we're getting to a point where left and right are equally tempting, whereas up and down look terrible, but it is in a point. But it always tends to be when it's still really short, so I ought to be able to drop out some numbers and write some more unit tests and find out what's happening. Watch this space.
So now it knows where the apple is.
I haven't told it where the apple is. It can only see what's immediately up, down, left and right. But I have cheated. I have given it the horizontal and vertical displacement to the apple. So that was the char state struct I showed you just now. Now, absolutely, I am cheating at that point. Various larger outfits funded by some of the large companies have got together the OpenAI gym and then various other learning environments where you can download emulators for specific games and set up some reinforcement learning. Some of it on Q-table-based stuff, but then you can choose what goes in the tables. And the better ones that don't do that silly wiggling thing that I just demonstrated to you that I don't know why is happening, the better ones, they won't use a Q-table. Because if you think about the state that's going on there, there's a lot. It's doing all right this time, isn't it? Yes. There's a lot going on there. But what a lot of these AI libraries will give you is it will take the last 5 frames and build a convolution neural network over that, which is just a way of saying what's tending to be near to what and allows it computer vision. It can't really see in the same way mine can't really see what's around each pixel, but it looks at the last 5 frames. And then it's got a sense of where its tail is and what to avoid. And it sends them through a neural network rather than just putting them in a map. That's less embarrassing than the first one, though. That's not bad. And that's just with a map and using some pretty naff-looking code to pull out a number and what to do. Cassie, I think I've got a couple of slides left, and then I might kick that off again. Yeah, in fact, that is probably nearly it. So the reinforcement learning is just one type of AI. And look, we haven't gone through, like, deep neural networks, convolutional neural networks, large language models, or anything like that. We've just built up a table remembering what happened or what reward you got last time you tried this. I've had to intervene with the state and give it, well, I think it's completely fair seeing what characters are around the head. I have told it nothing about Snake. And the thing about the machine learning games, no, the arcade learning games, is the people who came out with deep Q learning, they call it. So it's like Q learning, but it's using a deep neural network instead. Use the same code and then played Snake and Asteroids and Space Invaders and all kinds of different games. And that feels more like proper machine learning. We've set one thing up that solves lots and lots of problems. Go play around with it. And actually, for me personally, like looking back at the code and going, oh, I need to make my random number code better was useful. The slides have got some other resources in, but the OpenAI gym and the arcade learning environment are amazing. And like, there's a YouTube of this kind of thing, but that based on the deep Q learning rather than just the Q learning I've done. Watching it learn to play Pac-Man and getting it completely wrong to begin with and then getting better. It's cool. So I've been me. I'm going to kick off another Snake demo. Take away from this is practice coding. Look at your code, and if you need to code than me, then come and help me out. And also, when someone talks about AI or machine learning or something you think you don't know anything about, often there is an easy way into it. And if 2 dimensions is too hard, well, hang it, start in 1 dimension. If you're finding something difficult, solve a different problem, find a simpler problem to solve instead. And that might just get your head in gear. You might actually be able to understand this if you put your mind to it. And my snake might embarrass me again. It's going to, isn't it? I have no idea why it does that random zigzag. So we've got a few minutes left. I'll leave that playing. If there's a question, and if there's not, we can just chill and watch Snake and you can chat to me after.